Hello, people. Now, welcome to another Benito's explanation revision video to basically help me revise, because let's be honest, I don't really know that much. This is just my method of the revision, and hopefully it'll help you as well, so we can learn together. Isn't that lovely? Now, it's been a long time since I did one of these, and this is the first one I've done of physics. Yeah, this is the AQA AS Physics syllabus. Should have said that. And the exam's almost 2 weeks away, so we better get on with it, really, haven't we? But hang on. Before we do that, we have to get our priorities right. As you can see here on the board, Into the West of Oxfordshire Series 2 Episode 1 was uploaded 6 days ago. And in those 6 days, it has already clocked up 102 views, so thank you to everyone who's put it on Facebook and blah blah blah. Now, usually when I put a video which I want a lot of people to see, I wait a long time before I upload my next one, so it gives people a chance to see it. Unfortunately, with these exams coming up, I can't do that. So, basically, if you're watching this video now, stop watching it and watch Into the West. We have to get, basically, Into the West is more important than your education at the moment. Okay? I just thought I'd say that. I mean, I'm not pressurizing you or anything, but no, on a serious note though. Yeah, I mean, yeah, watch it. Yeah, watch it. Yeah, watch it. So, now we're going to be doing a bit of quantum phenomena today. That's half of the video time gone. No, because I'm quite proud of Into the West. Anyway, so, we're going to be talking about quantum phenomena, and we're going to start off with the theory of photoelectricity. Now, just randomly thought I'd write the title up. Now, the photoelectric effect is the thing we see when we emit radiation onto the surface of a metal, and the metal emits electrons. You must remember, if you do chemistry, you'll know this. A metal is just composed of positive ions, but it's held together by a sea of delocalized electrons, which are allowed to move freely in the metal. Now, these electrons are allowed to escape from the metal when they're given enough energy. So let's see, we've got a frequency of radiation here. Now, it is the frequency of radiation which affects the energy of the photons emitted on the metal surface. Remember, photons are the little packets of energy of light. Because if we look at this equation here, which we've probably seen before, E equals hf, where f is the frequency and h is Planck's constant. It's one of the smallest numbers. It's 6.63 times 10 to the minus 34, one of the smallest numbers ever, and it's joules per second, I think. Anyway, so yeah, the frequency of this radiation must be above the threshold frequency. That's the minimum frequency required to relieve an electron from the surface of a metal. Now, so that means the photons will have enough energy to overcome the work function. Now, the work function has a funny symbol. It's basically a 0 with a line through it. That's work function. Now, the work function, whilst the threshold frequency is a property of the radiation, the work function is actually a property of the material. It is the energy required to remove an electron from a specific metal, because obviously electrons are hard to remove from certain different metals, so they each have a different work function. Now, what's quite interesting is that the electron emitted is, well, actually, let's start with the basics. One electron in this atom absorbs one photon of light, because the energy of the electron is exactly the same as the energy of each photon hitting the radiation. So that means, well, it means that, well, we're going to get into this into more detail later, but light here is acting as a particle, because electrons are absorbing one photon. It's not just a wave of light that's hitting it, because that would mean if we increase the intensity of the radiation, that would cause the electrons to be emitted from the surface, regardless on whether they exceeded the threshold frequency or not. The radiation exceeded the threshold frequency. Electrons will only be emitted if it's above the threshold frequency. So that means if you increase the intensity of the radiation and the radiation is below the threshold frequency, absolutely nothing will happen. It's all about the energy of those photons, because one electron absorbs one photon. So we're saying that light is acting as a particle, not as a wave. Right, hold on. Now, the kinetic energy, so electrons are being emitted from the surface here. Now, the kinetic energy of these electrons is given by HF, that's the energy of the photons, take away the work function, that's the energy required to remove the electron from the metal. So, basically, let's say there's an electron here. The kinetic energy here is going to be the energy of the photon, take away the energy that was required to take the electron from here to here. Yeah? Does that kind of make sense? So that means if we just do a simple rearranging, that the energy of the photon is the kinetic energy of the photoelectron plus the work function. There we go. And we can do even more rearranging here. Well, not, it's a bit different this one. The threshold frequency can be calculated by the work function over Planck's constant. Now, one thing that I have been aware of that comes up in past papers on a lot, but doesn't come up in the textbook, is the formula for kinetic energy. And this occurs in the mechanics section, which is in Unit 2. So this is why I'm revising Unit 2 as well as Unit 1 at the same time, even though the Unit 2 exam is still a few weeks away, because some of it may pop up. So, kinetic energy is half mv squared. Remember, kinetic energy is energy of movement. Kinetics is the study of moving things. In chemistry, it's the study of rates of reaction. But anyway, so we know the mass of the electron. That's given in the formula book, which you'll have. And they'll probably give you the speed, so you just need to do half times the mass times the velocity squared. There we go. Anyway, just thought I'd point that out. So, now, if we did a graph, right, of a frequency this end and energy this end, we should get a completely positive correlation. We should get a straight line, right? Now, the gradient of this line should give us the Planck's constant. So it's always constant. So, because if we rearrange this equation here, we get h equals E over F. Remember, the gradient of a line is the change in Y divided by the change in X. So we're doing change in energy divided by the change in frequency. Exactly what this is showing over here. So that's what's going to give us Planck's constant. The part where it touches the y-axis is going to give us the work function of the metal. And where it crosses the x-axis, it's going to give us the threshold frequency. Now, what are we talking about now? Collisions of electrons with atoms. Ionization is when an electron is knocked off an atom. So, to form an ion. Ions are charged atoms. They carry a charge because an electron is added or removed from it. But in physics, we're talking more of electrons being removed. So, this means they can be very reactive. Now, sometimes, when we're talking about energy in particle physics, we can express it in different ways, and a way that's often used is the electron volt. Now, in electricity, we do voltage equals energy over charge. To get from joules, which is the energy we've been using so far, to electron volts, we do exactly the same. We do our energy divided by the charge of the electron, which is 1.6 times 10 to the minus 19 coulombs, and that will give us your electron volt. Now, sometimes the energy required for an atom, this isn't about photoelectricity, by the way. Can I just point that? Okay, we've gone to a completely different subject. Hopefully you got the gist of that. Now, sometimes the energy required at hitting an atom isn't enough to completely ionize it. It just gets the electrons a little bit more excited. And this is called excitation energy. So if we've got our atom here, now we know that our electrons are in fixed shells in the atom. Sometimes they're given a little bit of energy to move up to the next energy level. Moving up to each energy level requires more energy. So these electrons get excited, they absorb the energy and move up to here. Now, this isn't very stable. So before you know it, that electron is going to move back down to the shell before, or energy level. We normally call them energy levels. Now, in the process, it's going to release the energy which it gained, and it's going to release that as a photon of light. And that makes this very useful in fluorescent lamps, because gas can be made to glow, right? It's a mercury vapor lamp. Basically what happens is you've got your load of mercury vapor in here, and you emit electrons at the vapor. Hang on, no, is this right? Hang on. Right. So you've got a load of mercury vapor and you're emitting electrons through the mercury vapor. These electrons hit the mercury atoms and excite them. So the electrons here move up to higher energy levels. Then they move back down to low energy levels, giving off photons of UV light. Now, along the layer of the fluorescent lamp, you normally get a sort of sodium layer. These are UV photons which have been emitted from the mercury atoms. Go excite the atoms in the sodium layer. Now, obviously we can't see UV light. In fact, it can be quite dangerous for skin cancer, etc., etc. So it's important that we get rid of that. Well, what happens? The sodium atoms actually absorb, get excited, and then when they de-excite, they fall back to their energy level, they'll release visible light, which we can see. So that makes it all very useful and we're all happy. So the energy required to move up to higher energy levels gets higher as you move up and up and up. So, and you can see when electrons move down, as you can see, when electrons move down from sodium, they emit a different wavelengths of light than they did when electrons move down from the atoms of mercury. So that means each element has its own line spectrum, a spectrum of wavelength which it emits when electrons are de-excite, which allows us to identify it's how helium was discovered, for example. So that's all very useful, and I think, well, I've gone over it very, very briefly there. So yeah, so help yourself to more goodies in the textbook. So I hope that was okay. I think I did quite well there, even if I do say so myself. I don't know why. But hope you find that useful. Oh, and by the way, I almost forgot, right? Into the west, into the west, into the west on my channel page. Into the west, into the west. I'm going to drum it into your head, because if you haven't quit this video yet, you're going to see it now, aren't you? Into the west. On my channel. Go to my channel. The link's below. Thank you very much.